Hello class, it's time to start the discussion on alterations of nutritional status. I have an alternative book that I've used for my physiology class as a supplement book that is actually a lot better to use than our official textbook. Basically, this chapter is dealing with energy balance or homeostasis of energy balance. This is different than maintaining other balances in the body because our energy input means our food intake, and the problem is our meals are very intermittent. And as such, in between meals is actually perceived as a type of stress to the body. You're going to see that several stress hormones can play in these altered nutritional states. There is a lot of biochemistry involved in this, but I hope that I can make it easier for you to approach and wrap your brain around it. We should probably review what our macromolecules are and what our monomers are. Our three main nutrient classes, foods that we eat, are carbohydrates, proteins, and lipids. We are not going to really entertain nucleic acids because they don't have high nutritional value, and you really don't store them to use for energy sources. Carbohydrates, of course, involve sugars, and the monomer is glucose. And in our bodies, we store it as a polymer called glycogen. A picture of glycogen is seen here in the bottom left of your screen. Proteins are, of course, derived from amino acids. We absorb them from our diet. Lipids come in a variety of different forms, but for our purposes, we are going to talk about triglycerides, which are a glycerol backbone with 3 fatty acids attached to it. If you're talking about a diglyceride, it is a glycerol backbone with 2 fatty acids attached. And a monoglyceride would of course be 1 fatty acid attached. A picture of the formation of a triglyceride is shown in the bottom right of your screen. After you ingest food, your absorbed nutrients can be used immediately for energy, catabolized, oxidized for energy, or they can be used to synthesize new novel molecules that the cells may need, or they can be converted into a polymer to be stored for future use as an energy source. Let's talk about the fate of glucose. Well, you can ingest carbohydrates in many different forms, and your digestive system has a series of enzymes that will break down those polymers into absorbable monomers. And the classic one is glucose. It is not the only one. There are others like fructose, etc., but I'm going to focus on glucose. Once glucose has been absorbed, glucose can be used right away for energy. Of course, it would be entering glycolysis. If there is oxygen present, it would then enter the Krebs cycle as pyruvate. All of this is discussed in the metabolism lecture from physiology that I uploaded as a review in case you need it. If there is excess glucose that the cells don't need immediately as an energy source, it can be stored as a polymer called glycogen. Your liver and skeletal muscles have only a few hours worth of this polymer to be used as a supply for energy. Neurons do not have the ability to store glycogen. As such, they need a steady state supply of glucose in order to maintain cellular function. Also, glucose can be used to create polymers like polysaccharides that are used for structural support or for tags on the surface of cell membranes for identification purposes known as antigens. So they don't necessarily have to be converted into the storage energy form glycogen. They can be used for structural support. I just want to remind you that this step of glucose entering the cells, the first step in glycolysis, is adding a phosphate group to turn glucose into glucose 6-phosphate. This helps trap the glucose inside the cell so that it cannot escape, and the cells can then act on that substrate and use it to release stored energy by breaking bonds and then converting the energy released from those bonds into recreating ATP, which is, of course, the cellular form of energy. On this picture, I'm showing you how glycogen can be broken down in skeletal muscle into glucose 6-phosphate. Unfortunately, skeletal muscle does not have the enzyme to convert glucose 6-phosphate, or G6P, back into regular glucose. In skeletal muscle, it would have to enter glycolysis and turned into pyruvate to be used for energy purposes. The G6P could not leave the skeletal muscle cell in this form for other cells to use the glucose as fuel. But other tissues, like the liver and kidneys, they do have an enzyme to convert glucose 6-phosphate into regular glucose, which can be released from the cells and then be used by other cells as a fuel source. Let's now move on to proteins. Of course, we have peptidases that are enzymes in our digestive tract that can break down the proteins that we ingest into smaller peptides or single amino acids. Just to remind you from your physiology class, you probably learned about the enzymes released from the pancreas that help with protein digestion. For example, procarboxypeptidase, trypsinogen, and chymotrypsinogen. All of those are zymogen enzymes, and they are converted into active enzymes to break down proteins into smaller monomers or smaller peptides. Once you absorb the amino acid, it can circulate in the blood and be incorporated into the cells of the body. Amino acids can be used to build proteins all over again. Catabolism of cellular proteins to generate energy occurs only during periods of starvation, and it generates ammonia and carbon dioxide as waste products. The ammonia is converted by the liver to urea, which is eventually eliminated in the urine. If you look at the reaction up here on the slide, it is showing you glutamic acid reacting with oxaloacetic acid, which is actually an acid involved in the Krebs cycle. Deamination means that you are removing an amino group from the amino acid. What you are creating is a brand new novel amino acid, in this case aspartic acid. But you are also creating a keto acid, the alpha-ketoglutarate. Amino acids are only used for energy during times of starvation. As such, it comes at a price because it is going to lead to the synthesis of keto acids. This will lead to ketoacidosis, which means a lower than normal pH. This is, of course, metabolic acidosis. What about lipids? Well, we absorb lipids, and the lipids that we absorb have several fates. Triglycerides are going to be transported in the bloodstream as lipoproteins, and triglycerides found in the very low-density lipoproteins at the outer surface of the cells can be broken down by an enzyme called lipoprotein lipase. This enzyme breaks down triglycerides into fatty acids and monoglycerides. I will remind you that fatty acids are long hydrocarbon chains that can either be saturated or unsaturated. So the fatty acids can be taken up by nearby cells, but any monoglyceride that remains in the bloodstream is going to have to go to the liver to be further processed. So what happens to the fatty acids once they get taken into the cells of the body? They can be used immediately for energy. I will remind you that fatty acids can be broken down through the beta oxidation process, which is a multi-step process, and I reviewed that in the metabolism lecture for my physiology class. It is a multi-step process, and the end result is that the fatty acid chains are cleaved into 2 carbons at a time, and they can enter the Krebs cycle. They are going to enter in the cycle as acetyl-CoA. The fatty acids that are taken in by the cells can be used to recreate triglycerides in the cell. The cell would create its own glycerol backbone and then attach 3 fatty acids to it and use it as a storage monomer. Fatty acids can also be used to derive phospholipids, which are important for the cell membrane. Phospholipids consist of a glycerol backbone and 2 fatty acids. Cholesterol is another lipid, and it is used in several ways, one of which is to act as a precursor molecule for steroid hormones. Here is just a quick review showing you what can happen to the monomers that you absorb. Glucose, shown here on the left, can be taken in by the cells. The purple dot that you are seeing on the surface of the cell represents a glucose transporter, an integral protein that will help incorporate glucose into the cell. Shown here in step 2 for the glucose pathway, it can be used immediately as a fuel source. It can be oxidized into carbon dioxide, water, and energy. That means cellular energy, like ATP. Glucose can be used for the synthesis of other molecules that can participate in metabolism. I will talk about how glucose can create other molecules. For example, how glucose can actually be used to create fat molecules. And then finally, glucose can be used as a future energy source by creating the polymer known as glycogen. Amino acids can enter the cell. They can be used as monomers to create new proteins, but they also can be catabolized to generate carbon dioxide, water, and ammonia. The ammonia will actually go through the bloodstream and enter the liver and be converted into urea, which can then be filtered by the kidneys and released in the urine. Lastly, the fatty acids that you absorb from your diet can be carried through the bloodstream through lipoproteins, very low density lipoproteins, etc. These fatty acids can then be incorporated into the cells and used immediately for energy, as shown here in the bottom of Part C. Or they can be used to recreate new triglycerides, which are a storage form of lipids. Later, when the metabolic demands are great, these triglycerides within the cell can be broken down into monomers like fatty acids and glycerol, which both can be used as precursors to enter the Krebs cycle. Any monoglyceride that remains not processed by the adipocyte can go to the liver to be further processed and metabolized. This is a nice table to show you how we absorb different monomers for each of the three macromolecules that I just addressed: carbohydrates, proteins, and lipids. You can see here how they circulate in the blood, how they can be stored in the cells as storage molecules, and where exactly in the body they are stored. Now, it should become very apparent to you that the best way to store our storage molecules is in the lipid form. Unfortunately, they are not easily mobilized. It actually takes some time to mobilize the stored lipids. But once they are mobilized, they are an amazing fuel source. Carbohydrates are our first primary fuel source that we want to use, but we don't have a lot of it to sustain life or basal metabolic rate beyond a few hours. We do have proteins that can be used for an energy source, but these are highly conserved for structural support. So they really are not used as an energy source unless there is starvation involved. Energy, like anything else in the body, needs to be maintained at homeostasis. To be in balance in this context means that what comes into the body and what is produced by the body must equal the sum of what is used by the body and what is eliminated by the body, as shown. Input plus production equals utilization plus output. In terms of energy balance, the body does not produce energy, an impossibility according to the laws of thermodynamics, and so this equation becomes energy input equals energy utilization plus energy output. Energy is used by the body to perform work, and energy output exists as heat released. Therefore, the balanced equation becomes energy input equals work performed plus heat released. Now, how much of the energy output is heat? And how much of the energy output is work? About 60% is heat, and about 40% will be used as work. I am going to describe how the body can use that energy as work. Now, this balance is going to be regulated, highly regulated by the endocrine system. It is important to note that when we utilize our energy stores, they need to be replenished. They can be replenished by either us taking in more food or mobilizing our energy stores. That means taking our large macromolecules and breaking them down into smaller monomers. When we talk about burning our molecules, we are going to burn them through oxidation. But we can literally take a pound of butter, we can literally take a bag of sugar, we can literally take a steak, and we can put all those things on our barbecue. We can light a fire and we can burn them. If we burned all of that food in a container, we could actually measure how much energy is given off as heat when the steaks, sugar, and butter are actually oxidized. A calorimeter does that. It's like a barbecue that is contained that can actually measure how much energy is given off in the form of heat. Our body is a lot like that system, but of course we don't just liberate the stored energy in those chemical bonds as heat. We actually convert some of that energy into cellular energy. But our body is not 100% efficient. We are not perfect machines. So when we burn our fuel, when we oxidize it through glycolysis, the Krebs cycle and the electron transport chain is actually very inefficient. Most of the energy stored in those bonds is released as heat, 60% of it on average. The rest of it can be used for work, and that means we can use it for mechanical work, chemical work, and transport. When we are talking about mechanical work, we are talking about myofilaments, actin and myosin, creating contraction in our skeletal muscle or cardiac muscle, and smooth muscle. Chemical work can be the formation of bonds, like tying together exergonic reactions to endergonic reactions, reactions that release energy tied to reactions that need energy to work. Transport work means moving molecules from one side of the membrane to the other. The classic example would be the sodium-potassium ATPase. So when we oxidize our nutrients, we release the stored potential energy in those molecular bonds. We release primarily heat energy, but the other amount of energy we trap and create cellular energy, ATP. When we hydrolyze ATP, again, a lot of that stored potential energy will be released as heat, and the rest of it can be used to do cellular work. Now let's talk about eating and working out and gaining weight and losing weight. I just said that our energy output is going to be either the work we performed or heat released, and the two of them added together will be our energy output. When we are talking about energy balance, we're talking about energy input equaling energy output. Substituting this into the master equation means that our energy input, if and when it equals work performed plus heat released, means we are in energy balance. If our energy intake exceeds our energy output, that means you are in a positive energy balance. That means you are going to have a lot more storage molecules. You're going to have more weight gain. If you are in a negative energy balance, that means your intake is less than your energy output. You are going to burn a lot of your storage molecules and you are going to have weight loss. So again, if you are at energy balance, you are not gaining nor losing weight. Most of us would appreciate being in a negative balance where our caloric intake is more reduced compared to our energy output. Let's explore energy balance in more detail. Energy balance varies during two different phases called the absorptive and post-absorptive states. The absorptive state, simply put, is about 3 to 4 hours after your meal. Your stomach is still full, and let me make this clear. A lot of students think that 3 to 4 hours after a meal, I'm hungry again. No! 3 to 4 hours after a meal, there is actually still food in your stomach. You're still actively digesting what you've already eaten. You still feel the presence of food in your gut. You're consciously aware of that. That means you still have plenty of nutrients in your bloodstream from the absorption, and most of your body cells are going to make those monomers and form polymers and store the potential energy in the form of macromolecules. The post-absorptive state is the period when nutrient absorption is not underway, and your body must rely on internal energy reserves to continue meeting its energy demands. You spend roughly 12 hours each day in the post-absorptive state, although a person who is skipping meals can extend that time considerably. Metabolic activity in the post-absorptive state is focused on the mobilization of energy reserves and the maintenance of normal blood glucose levels. So our energy input is very intermittent. Our body is very good about storing our excess for times when we need to tap into those reserves. The post-absorptive state is between meals. I mean really between meals, when you are starting to feel hungry. At this point, your macromolecules are mobilized. They are catabolized into monomers. This means you need to mobilize those monomers into the bloodstream so that the cells of the body can use them for oxidative processing, basically catabolic reactions. The picture above shows how the body mobilizes your stored energy fuels in the post-absorptive state. Due to its high energy content, the adipose tissue represents a disproportionate percentage of the total reserve in the form of triglycerides. Most of the available protein reserve is located in the contractile proteins of skeletal muscle. Carbohydrate reserves are relatively small and sufficient for only a few hours or, at most, overnight. Simply put, during the absorptive state, we are talking about energy input exceeding output. That means you have plenty of monomers to go around. First of all, glucose will be used as a primary fuel source for every cell in the body. Anything that is excess will be taken up and stored. The liver and skeletal muscle, these are the biggies, will take up any excessive glucose and convert it into the polymer known as glycogen. The adipose tissue will take up any excess fatty acids and bind them to the glycerol backbones within the cell to store them as triglycerides. All of this is a preemptive strike to the post-absorptive state that is soon to follow. Let's talk about specific monomers during the absorptive state reactions. First, glucose. It is the primary fuel source for the cells of the body. Most of the cells of the body are insulin dependent. They need insulin in order to insert glucose transporters so that they can absorb glucose from the bloodstream. Insulin doesn't only allow glucose uptake by insulin-dependent cells, but we will discuss these other actions at another time. Specifically, glucose transporter 4 is the one that is inducible by insulin. In the liver and skeletal muscle, we are going to see excessive glucose turned into the polymer glycogen to be used as a storage molecule. Interestingly, if there is really a lot of glucose, the liver can convert the glucose to fatty acids, which can then be stored as triglycerides. So if you are on a high sugar diet, or maybe you're drinking alcohol excessively, alcohol has a high sugar content, it can actually lead to more fatty acid synthesis. That is part of the reason why we think of people who drink a lot as having a beer belly, because they have a lot of that subcutaneous fat. The fatty acids that you absorb from your diet can be converted in the cells of the body to triglycerides. Again, just to remind you, the cells would provide the glycerol backbone and then attach the fatty acids to that backbone that were absorbed from the bloodstream. Amino acids are going to be used primarily as structural monomers. They're going to be used to recreate polymers, but there can be times when amino acids will be used as a fuel source. A few of them can actually be converted into metabolites that can be burned in the Krebs cycle. Most of the time, though, the muscle cells are going to use the amino acids to build new myofilaments like actin and myosin. Although large amounts of protein can be mobilized for energy without serious consequences, particularly from skeletal muscle, continual use of protein for energy is harmful and potentially fatal, because it eventually compromises cellular function.